Thanks everyone for being here for our next EER seminar for the fall semester. Really excited to introduce my colleague, Professor Erin Johnson, from the EER program, as well as the Department of Aerospace Engineering here at Michigan. So Erin is a Michigan fan for sure, having done his undergraduate here, his undergraduate degree, as well as a postdoc position at the University of Michigan in engineering education research, and now as a faculty member since fall 2021, joining back the faculty at Michigan. Has also completed his PhD at MIT in aerospace engineering, as well as completed a postdoc at Tufts and a teaching position at the University of Colorado Boulder. Did I get all that, Erin?
Yeah, good job.
Thank you. So really excited to have Erin share some of the work that he's been doing. I think a lot of you in this room and online know Erin as a fantastic instructor as well as researcher and also mentor, and I'll add a fantastic colleague as well. So really grateful to have you here giving this presentation. Thank you, Erin.
All right, thanks for having me. I'm glad I don't have to tell you where Karen went to school. I'll have to study up on that. But super happy to be here and super happy to be talking with you all today about some of the stuff I've been doing and thinking about. I don't need a job, I don't think, so you should all hire Dr. Joe still, but I am trying out some new ideas in this talk, some new arguments, so I do welcome sort of feedback in that regard. All right, so, why isn't this? Let me try to reset this. Whatever, I have to stand here with the camera anyways. All right, so before we begin, wanted to start by saying a few things. First, I think it's important to remember that you do not leave yourselves at the door when you enter this space and engage with this talk. And that's really a good thing, that we all have those different backgrounds, perspective, positionalities that we bring here. By the same token, maybe there are other things on your mind this week. I know there are for me. I didn't realize when I got this voting sticker that the werewolf is actually screaming in agony, but apparently that's what's going on. So I think it's important to talk about essentially my positionality, who I am, and how I approach my research, teaching, and facilitation. It is certainly influenced by my identity as a straight white man from a privileged background, a good school, with a privileged engineering education. But I want to go deeper than that. So the approach that I take to my work is really a critical emancipatory approach, really focused on systems of power. And in my work, I really want to specifically work to address the root causes of systemic oppression. And one of the ways to do that is to work to help students develop what's called critical consciousness, which is the ability to recognize and work against oppression. And really my goal, my aim, what I'm trying to work towards is to take action and transform our oppressive systems that exist today, both in engineering education and more broadly. There are a lot of ways to work towards change, though, and work towards transformation. And Oluwakemi Johnson is the newest PhD student working with me. We were talking in EER 601 earlier this semester, and she essentially asked me, Erin, what is your approach to change? Is it using the master's tools to dismantle the master's house, or are you trying to burn it all down? And these are actually valid, and not that phrasing is illegitimate, but these are different theories of change. On the left, we have interstitial transformation, which is where you try to create change from within the system. You try to create pockets of like-minded people who are doing things differently within the broader oppressive system, and then you work to try to grow those interstitial aspects and change the system from within. On the other side, we have ruptural transformation, which maybe you can guess what that is from these images. That's when you have a break, you confront the system, you create a new system. It's often aggressive, an aggressive transformation. So really the way I approach change is sort of all throughout the spectrum, depending on who I'm talking to and what I'm doing. If I'm doing lessons in a class that people essentially have to be at, or if I'm talking with all faculty about what I'm doing, then I'm more on this interstitial side where I'm working more within the system. If I'm doing something like opt-in dialogues, like we just had a lunchtime dialogue about macroethics, over lunch, or if I'm doing faculty development where people have signed up to come, then we can be a bit more confrontational, a bit more radical. And then when giving seminars like this, when people are coming to hear my thoughts and my opinions and my work, or when I'm at the Michigan and Friends ASEE happy hour, then I'm definitely more towards this side of the spectrum and more confrontational. In fairness, I am not where I want to be. I will say when I'm in an aerospace faculty meeting, I am often kind of off this chart, right? There are reasons for that. We can debate whether or not they're valid. That is something I'm trying to work on, use my power and my knowledge and my position and be more confident to push for change in places where I feel less comfortable currently doing so. So in all fairness, that's something I'm currently working on. But today, given everything that's going on, I am on this side of the spectrum. So trying to be challenging in a constructive way, in a good way. Making this presentation was challenging to me. And I hope that some of the ideas in it and some of the research and the conversations are also challenging to you, right? Because it is good to be challenged. We should not shy away from that. Also, I will point out we have this neutrality policy at Michigan that says the university can't talk about things, but they do say that faculty can talk about what they want, and they are welcome to oppose the institutional orthodoxy. So with the regent's blessing, that's what I'll be doing today. Probably not in the way they intended this statement to be taken, but we're going to do it anyways. All right, so with that sort of background, where I'm coming from and what I'm hoping to do, I want to get now into what we do in my lab, the shuttle lab. So the fundamental premise of our research is really that engineering practice is messy, but engineering science courses are tidy. So this is really something that motivates most of the work that we do in the lab. So in this presentation, I will talk about what I mean by messy and tidy. I will talk about our work to put some of the messiness back into engineering science courses. And I should explain what those courses are. Those are the non-lab, non-design courses that students take in their sophomore and junior year. So here at Michigan, it's pretty much most of the 200 and 300 level courses. Statics, dynamics, gas dynamics, thermodynamics, circuits. I'm sure there are others in other disciplines that I'm not even familiar with, but those types of classes. I'm also going to talk about our research on how students think about one particular type of messiness of engineering related to mathematical modeling. So in these engineering science courses, we usually ask students to solve textbook problems. And so this is the audience participation part of the talk. What do you think of when you hear the phrase textbook problems? What is a textbook problem to you? No right answer to this. Yeah.
Find the only correct answer in the back of the book.
There's a one correct answer. It's in the back of the book. What else? Yes.
There's typically only one way to solve a problem.
One way to solve the problem? Maybe one more? Yeah.
I think it's related to what you just said, but so it's only going to use skills that have been taught in some preceding.
Yeah, right. It's like take what you just did in the previous week and apply it to something that maybe looks a little bit different than something you did in class. Yeah. So textbook problems, I would say, I use the word tidy. I think they are tidy. And so what I mean by that is that they're well defined and they've already been simplified to the assumptions of the theory taught in class, as we heard about. So this is an example from orbital mechanics, which I taught when I was at Colorado. It's asking you essentially to find the amount of energy a rocket needs to change its orbit around Earth. There is one answer to this. This is well defined. You use a certain procedure called a Hohmann transfer, which is the minimum energy transfer. It assumes that your rocket fires instantaneously, which is not actually how a rocket works. It fires over a period of seconds. But this problem, makes that assumption that conforms to the requirements of this sort of simplified transfer. These problems, textbook problems, they're closed-ended, they have one correct answer. They're often decontextualized and have no physical meaning, right? So we're trying to send a satellite from low Earth orbit to a higher orbit. Who is doing that? What kind of satellite is it? How is it going to get back down when its mission's over? None of that is really talked about in this problem. Textbook problems being tidy does not mean that they are all simple, right? Textbook problems can be complex, right? So this is another orbital mechanics problem. You have to calculate the energy needed to get from Earth to Mars. When I did this in class, it took me 7 slides to solve. There's a lot of steps. There's like at least, what is it, like 6 steps at least, 5 or 6 steps. You gotta account for like a whole bunch of variables that you calculate here and then you use here. So this is a complex problem, but it is still a tidy problem. It's simple, well-defined, and one answer. Engineering problems in engineering practice, those problems are different. So another audience participation moment. What do you think are characteristics of real-world engineering problems? Yes.
Not assuming that it's all ideal properties.
Okay, not all ideal properties. What else? Yeah.
A lot of the times there's a human factor.
There's a human. Yeah, there's a person. Yeah. Maybe you have literally human factors or ergonomics, but also maybe there's other ways it impacts people. One more. Yeah.
You have to think about the step before and after your design.
Yeah, you have to think about the broader context, the step before and after the design. Yes, exactly. So in engineering practice, the problems are complex, but the problems are also messy. And what I mean is that, to start, they are ill-defined. There are conflicting constraints. There are conflicting outcome metrics. There's not just one right answer. Right? They are open-ended. There's many possible solutions. There's also many different methods to analyze the system, right? There's many answers. There's many ways to get to those answers and do the modeling and do the design. Real problems are also messy in a socio-technical sense. They affect people, and they are affected by people in both positive and negative ways. So I think, like you're saying, we have to consider what happened before and what's going to happen afterwards with our engineered system. So this is the reality of engineering problems. They are messy. So when do students have a chance to learn about this messiness in their engineering work? Well, one place is during co-curricular internships, co-ops, and project teams. Really good chances to work on a real project and gain some real experience. A problem is that not all students can participate in these activities. Some students have to focus on classes. They have to work to support their family. They don't live on campus. They live in Dearborn, and they can't stay afterwards to do the project team meetings, right? And I think fundamentally, I ask myself this question, yeah, these are great, but why are we pushing messiness outside the curriculum? We should be talking about it inside the curriculum as well. We also do have design courses in our curriculum, and these are also really good places for students to learn about messiness. So this is the aerospace course sequence, right? Everyone takes Engine 100, so you get a bit of design there. Also, you have senior capstone design. And in Aero, we have a few others throughout, some lab classes, a systems engineering class. So there are opportunities, but I look at this and I look at this diagram and I look at, okay, when do we have design? When do we have messiness? Well, it's at the beginning and the end of students' education. What about all of these other courses in the middle? All of these engineering science courses? I believe and advocate for talking about messiness throughout students' education, right? I think we need to add a little bit of messiness in its various forms throughout the entire curriculum. And so why do that? What's the reason for doing this? Well, one of the first things is that students already, they know that engineering is messy. It's not like, some of them don't, but it's not a surprise to most students. This is a poster that's been up in the aerospace building. It's from a group, I forget the exact name, but it's like Aerospace Students for Disarmament, right? And it's a group of students who say, well, I really want to make things that fly, but I'm not excited to make weapons. And a lot of the funding in aerospace comes from defense companies, right? So these students recognize the messiness, sort of in a socio-technical sense, of engineering and the degree program that they're currently a part of. So they already know this, right? And if they don't, I think we need to tell them. Teaching students about messiness throughout their education also prepares them better for capstone design and then their future career, right? Because capstone is already busy. We have to teach them some technical communication, some professional skills. And if we also have to teach them how to deal with messiness, that's just one more thing we're adding on top of it. And we can't really give everything full shrift. So I think we need to start doing this earlier. Teaching students about messiness presents multiple perspectives that engineering students don't often get to hear. It also helps students to reflect upon their views and biases. And we can pretend that as engineers, we're going to be neutral or objective, but that doesn't really exist, right? Just as you cannot leave yourself at the door, you cannot leave yourself when you enter the door of your future engineering career. And your views and your biases are going to influence the decisions that you make, whether you know that or think that they will. And so it's good to help students start to reflect on that. Talking about messiness has the potential to increase retention and engineering identity. I think we can bring students, not just Michigan, but any engineering program can bring students in. We give them a really good Engine 100 course. And then we say, okay, you did well. Do 2 years of applied math, and I'll see you for capstone design at the end. And that, I think a lot of people leave because of that, because they're not doing what they want to. They don't feel like engineers by just doing a lot of decontextualized math. So teaching messiness, can push back against that. It also, teaching messiness, admits that engineered systems can uphold oppression. And so just some examples here. We'd like to talk about algorithms as being unbiased, but humans make algorithms, and algorithms are made with data that humans produced. And just as humans have biases, therefore those algorithms also have biases. We can talk about mining, lithium, right? The materials that we need for our futures. We had a conversation in our macroethics dialogue about AI and the amount of energy it uses, tremendous amounts of energy. And also in an aerospace example, future government official Elon Musk is wants to create a settlement on Mars. Somebody asked him on Twitter, how are you going to staff it? And he said indentured servitude, which maybe isn't bad on its face, giving people loans to go work. But, I think there's a lot of questions. Can you go on strike if your company provides the air that you breathe? Right? So a lot of ways that engineering systems can, and may uphold oppression. And we need to talk about that. As I said, not all students can obtain an internship or participate on a student project team. It also, talking about messiness, gives minoritized cultures a chance to be represented in engineering problems. So I think these are reasons why we need to engage students in messiness throughout their education. If I were to put different words on this, I would say that teaching students about messiness achieves our goals of diversity, equity, and inclusion. And so I make the argument that talking about messiness is a part of DEI. Now, I don't think it's all DEI. I don't think we should stop what we're doing, the great work we're doing about race, gender, socioeconomic status, disability, and replace that with messiness. All of that is critically important. But I do think that we should be making the argument that talking about this messiness is part of our DEI efforts. And I think it's easy to see how some forms of messiness, like the socio-technical aspects of messiness, like how those are part of DEI, right? Because we can talk about how engineering causes oppression or causes inequitable outcomes for people, like seatbelts, right? Seatbelts were originally designed for men and sized for men, and they had male crash dummies. And as a result, women were being severely injured in car accidents at a higher rate than men. So I think examples like that make it easy. There's a clear connection, at least for me, between those examples, the socio-technical aspects, and DEI. But I also think some of these other aspects of messiness, like around design and mathematical modeling, I also think they're a part of our DEI efforts, because teaching about that allows us to push back against the white supremacy culture of engineering. And I use the term white supremacy culture purposefully. And I was having a conversation with Betsy Strail and some of my other students about this. And they were really saying, this is what teaching messiness can do. And when I hear the phrase white supremacy, I think it's really easy to initially think of like groups that are like explicitly, violently, purposefully, maliciously like racist or sexist, right? And those do exist and are very bad, of course. But just our culture and our culture of engineering and our culture of engineering education research was built on ideas that really privileged and held at its top white, straight men. We have a lot of military background as well. This is just the culture of engineering education. It's not something that we created, right? We came into it after this was created. So it's not our fault. And it's not, I think this is important to say, it's not the fault of like white straight men in engineering today. I'm certainly not saying that people look like me are racist or intentionally malicious, right? But people that look like me, we benefit from this culture. So it's not our fault, but it's our responsibility to dismantle it. And so to get a bit more into that, I want to, there's some great references down here about what characteristics of white supremacy culture, and I pulled a few out. So the idea that there's only one right way to do things, that we need to be objective. Also this focus on individualism, this idea of quantity over quality, and either or thinking. So what does that look like in traditional engineering science courses, or when we're teaching textbook problems or tidy engineering problems? Well, we send students a message that there's only one right way to do things, as we heard about, right? And students just need to man up, and I say that intentionally, right? They just need to man up and learn it. Or we talk about individualism, right? Students, they're solving these problems alone. Maybe we let them collaborate on homework or something, but you have an exam where you just sit down and do it yourself. We talk about quantity over quality by valuing the output, valuing the answer above all else. And those answers, they're either right or wrong. They're not both. But we can work to break down white supremacy culture in part by talking about messy engineering problems. I also want to be clear, I'm not suggesting that messy engineering problems will end racism in engineering education research, right? This is an enormously complex and entrenched problem, right? But I think we have a responsibility to do what we can in our sphere of influence. And I think engineering science courses are one place where I know I have influence, and I think a lot of us have or will have influence as well. So we can, right, instead of saying, oh, there's only one right way to do things, let's be objective. Instead, we say, no, you need to develop and use your engineering judgment. You need to use judgment to solve engineering problems. And that's not objective, that's socially constructed. It comes from your experiences and your background, right? And that's a good thing. That's a good thing. Students need to work together. They need to synthesize multiple perspectives. It's not just about doing it yourself. It's relying on your peers and their knowledge and listening. Rather than just valuing the output, we need to value the process, right? How do we get there? What are the decisions that you made along the way? That's honestly what's more important than the final answer. And also we value relationships. We value working with others. And rather than saying, right, everything is right or wrong, sort of in a way that simplifies engineering, let's embrace the complexity, right? Engineering is complex. Engineering is messy. Let's embrace that. Let's not ignore that fact. So I really think that we specifically, as Michigan engineers, need to talk about messiness as DEI for a number of reasons. And there's a lot of conversations now, as there has always been, about DEI at Michigan. There's this New York Times article, and I very much disagree with the framing of it and a lot of things that were written. I mean, I do think, right, talking about the amount of reports we have to write for DEI, sure, I agree with that, but there's this big conversation. But I really think that we need to be having these conversations and we need to be talking about DEI. One reason is because as of right now, we can, and students in other states can't, right? I gave a talk at Iowa. Iowa is ramping down all of its DEI activities next month in preparation for a ban coming next summer. Same with our colleagues in Texas, Florida, Georgia, right? Ohio. We know a lot of people in these places, and they can't have these explicit conversations with their students. So we need to be doing it with our students. And who knows what the future holds nationally, right? Another reason we need to have this conversation is because DEI is used as a disingenuous attack against minoritized engineers and their work, right? You've probably heard Elon tweeting things like DEI is crashing Boeing planes, or right, presidential candidates being a DEI hire, right? Well, in engineering education and research, we're not immune from that. There was this report from the Senate Commerce Committee about a month ago talking about how the NSF is politicized because they fund DEI research, explicitly named some of our friends and colleagues in red states. I do not recommend you read this because it's very poorly written and it lies a bunch, but is that going to matter after January? I don't know, right? So I think especially those of us who are privileged in some aspect of our identity or are safe in our jobs or do live in a state like this, I think we have a responsibility to be talking about this and supporting our colleagues. And just fundamentally, messiness is a part of engineering, right? Whether we're allowed to talk about it, whether we're regulated, whether we don't get funding, I mean, that doesn't change the nature of engineering. It doesn't change the fact that students are questioning whether they want to be an aerospace engineer because they're from the Middle East, or right, whether students are saying, I'm just doing math. I don't know if I'll be an engineer. I can't do a project team. Am I going to be able to get a job? Right? Like, no matter what the regulations are telling us, we have an obligation to teach our students about the nature of engineering. And none of this above us is changing the nature of engineering. So I think it is unethical to pretend that messiness does not exist in engineering. Okay, I'm gonna take a breath. So that being said, this is not easy. I don't want to make it sound like this is easy. It is not. Whenever you give students messy problems or expose them to messiness, they get anxious because they're used to finding one right answer. So if you give them an open-ended problem, they're like, well, what's the answer? And you say, oh, there's no answer. And they're like, oh my goodness, they haven't done this like even in high school, right? They're taking math and science where there's one answer. So they get anxious. And they also have to work with their peers, integrate multiple perspectives. Also something that we try to teach them, but is hard. For faculty, this is hard as well, right? They don't know how students will think about messy problems. And it's hard to facilitate learning if you don't know what your students are going to be doing or how they're going to be exhibiting their thinking. You can't respond to them if you don't know what to look for. Faculty also don't know how to relate messy problems to the technical course content, right? How do we bring this messiness in? And do we just like pause our lesson on beam bending and talk about the military industrial complex, or pause it and talk about design? You know, how do we actually integrate this messiness into the already overstuffed curriculum? And also, faculty aren't trained to facilitate discussions about messy problems. It's just not something that we're trained to do, and that's hard, and that can be scary, right? I think another aspect of messy problems is that there's no answer, and so as faculty, we don't always have the answer. And it takes a lot to learn how to stand up in front of a class of 100 sophomores and tell them you don't have an answer. That's just not something that we are traditionally good at. Also, there's, racial and gender aspects to that as well. It's me as a white man standing in front of a class and telling them I don't know. That comes across differently as like a woman of color saying that, right? They're going to perceive us differently. So this is not easy. I think it is important. I think it is critical. I think it is our moral responsibility, but I think it's really hard. It is really hard. And I just want to acknowledge that. And so this is finally getting to what I do and what our lab does. This is really what we're working towards. We are trying to address these barriers and knowledge gaps with design-based engineering education research, so we can help faculty and students have more of these conversations in their engineering science courses. So design-based research is a particular type of research that is very closely coupled with practice. It suits very much my position here, being in the aerospace department. My background as someone with a PhD in aerospace engineering. I really like it. It really invigorates me to work so closely with faculty who are teaching. And so the way this research works is we first identify a specific need in engineering education, and then we develop a research plan. All right, how are we going to study that? And then you really have this sort of tightly coupled, hopefully upward spiral between research and education. And so at the end, what you do is you implement some new activities in class. You have a new assignment, or you have a new dialogue or something, a new lesson. And at the end, you have interventions that improve engineering education. That's not all. At the same time you're doing research, that gives you an improved fundamental understanding of learning in context, right? So we have this research and education happening at the same time. So the work in our lab addresses messiness in two forms. The first is mathematical modeling, and the second is macro ethics. And I'm going to focus on the mathematical modeling today because I just spent an hour and a half talking about macro ethics, and I wanted to talk about something different. Also, we have a lot of great work in engineering education research talking about macro ethics and the ways that engineering is socio-technical, and we affect people and are affected by people. So there's the T Center, right, through CSED, involving a lot of the EER faculty. James Hawley Jr. is doing a lot of this great work. The teaching equity teaching circles that CRLT is running and ran through BME. Professor Finelli's work with Susan Lord and Aaron Seck. There's a lot of great work that is happening on this socio-technical side. And if you want to talk to me about this, come find me. I will happily talk to you about this. But today, I am going to focus on the mathematical modeling. I'm going to take a pause, and then we'll get into it. All right. So this research was started by me and Professor Jess Swenson when we were both postdocs here at Michigan with Cindy. And I also have a grant now, a REEF grant with Professor Rachel Vitale, who is an mechanical engineering PhD graduate from here. She's now at the University of Iowa. And we are NSF funded, and my views, just as they are not the official views of the university, these are not the official views of the National Science Foundation. All right, so getting into this, I want to start by talking about what is mathematical modeling. So mathematical modeling, as we define it, is the process of using a set of equations to represent the behavior of a physical object under a set of assumptions. So let's unpack that. So there are really two components, and I'm going to use mechanics of materials examples, because that's a course I have taught a lot. I think hopefully we'll understand it enough that if you don't know it, you can still understand it, and hopefully you can translate this to your own sort of model in biomed or chemical or industrial engineering or wherever you come from. So the first part of a model is the theory of behavior. This is the physical behavior of the type of object. So say that you want to model an airplane wing in how it's bending under loads, right? So there's a bunch of different theories that tell you, how much does a beam deflect when it's loaded. One common one that we teach at the sophomore level is called Euler-Bernoulli beam theory. Is anyone who here is familiar with this? Raise your hand. All right, my condolences. Yeah, so this is essentially, it's a fourth order differential equation that relates the properties of the beam material, the shape of the beam, and the load on the beam to the beam's deflection. That's essentially what it is. So this is an equation that you can use to analyze how much is a beam going to deflect. Now, this equation has certain assumptions. You can only use this equation, this theory, if you have small deflections. You can only use this theory if you have lateral loads, which are perpendicular to the axis, right? So if the beam is coming out from my arm, it only works for lateral loads. If you have a load going like into my arm, into the board, you can't use this theory. All right, so we have this theory that we teach at the sophomore level. We have other theories that have fewer assumptions that we teach at the junior level, that we teach at the graduate level, right? There are many different ways to model, to capture the physical behavior of a beam. And so that is the theory of behavior. Then we also have the representation, which is the physical properties of the specific object. So for modeling an airplane wing, we have to parameterize it, right? We have to mathematize it. We have to say, okay, what is the shape of it? Where is the load? What are the dimensions of it? How thick is it? What is the cross-sectional shape of this beam? Is it a rectangular beam? Is it an I-beam? We have to mathematize the actual object. And that is another part of the model, the theory that governs the physical behavior, and then the representation of the specific object. Modeling is also part of the overall engineering design process. So here are a couple examples of the engineering design process, the Systems Engineering V, this model from Teach Engineering at the University of Colorado, and the Center for Socially Engaged Design model. Many different models, all sort of very similar. But in each of these models, there is a step where you actually have to make the thing, right? There's so much work and so much judgment and so much messiness in figuring out who your clients are and what do they really want and what are the requirements and what are the impacts and where do you source your materials. That is all important, but not what we're talking about here. What we're talking about is sort of when you get down to it and you say, okay, I have all my requirements, I need to produce an object that meets those requirements. And in order to produce that object, you want to analyze the behavior of the system. You want to say, okay, if I make the beam this size, how much will it deflect? What if I change it to this size? What if I change this shape, right? You're trying to say, okay, I want to predict the behavior of the system so I know what to make it, well, what will it look like? So modeling is a specific part of this design process where we're actually doing the development, the design, the creation. It's kind of lives in that part of the design process. So the practice that we look at when we look at mathematical modeling is called engineering judgment. And so engineering judgment, there's actually a study out of Pittsburgh that's a Delphi study to define what engineering judgment is, which sort of suggests to the state with which the community uses this word. There's a lot of different definitions. I think in general, the way I define engineering judgment is just informed decision making in open-ended dynamic problem-solving context, right? It's something that's used sort of at a high level in design. It's also developed through experience and expertise. It's sort of synonymous with expertise. So as a part of engineering judgment, you need to identify what's important, you need to make reasoned decisions, you need to determine what makes sense, use your judgment throughout the whole design process. Now, I know this is going to come as a shock to you, but students are not expert engineers, right? So there's an argument or there's a comment that says, well, how can students have engineering judgment? We make no claim that they can. What we look for instead is emerging engineering judgment, or you might call it the productive beginnings of engineering judgment. So these are students' actions that are likely to lead to disciplinary fluency, or in other words, what is age-appropriate engineering judgment? What can a sophomore do that is certainly different than what a practicing engineer does, but it's similar, right? It rhymes, or it provides a logical starting point where you can say, okay, they start here, and then with more experience, it'll grow into this professional engineering judgment practice. And as I said, we're specifically looking at mathematical modeling. So we note that in the wide space of all of these definitions by talking about the concept of engineering modeling judgment. So I'm going to talk about emerging, meaning it's age-appropriate student level, modeling, focus on mathematical modeling, engineering judgment. Took us about a year in our submitted JEE paper to figure out how to explain all of that, how we situate in the literature. So talking about the education side of this work, so what we have done is created a new type of problem called open-ended modeling problems. This is a type of project-based learning that engages students' engineering judgment. So in OEMPs, students create a mathematical representation of a real-world object. So we've done OEMPs with a pool lift, with the Nomad aircraft in the FXB lobby, Nathan Chen, the figure skater, a slide, and a greenhouse on the shores of Lake Erie. So we give students these real-world objects and ask them to analyze them. Students have to do that by applying a theory of behavior learned in class in order to generally size a part of the object. So we've done this in a lot of statics or mechanics of materials classes. So students are using static equilibrium or axial stress theories. But with Nathan, we were using the moment of inertia, angular velocity, and work. And then this greenhouse problem was in a fluids class, and they talked about centrifugal pump performance. And then students have to assess the reasonableness of their answer. And often their answers are unreasonable. They say things like the plane's landing gear has to be 2 millimeters in diameter. And I wouldn't fly on that plane. As a PhD in aerospace engineering, I'm telling you that is small. But it's not because the students messed up the math. It's because they are applying sophomore level theories to an airplane. And there's just assumptions they're making that aren't realistic assumptions for a real world object. So they get these answers that are unreasonable. That's a really good thing to tell students and to teach students, right? What are the limits of these equations? So we've run a lot of surveys. Students seem to like these. They seem to recognize the value. They think they are real engineering problems, right? Or like real engineering problems. They think these problems help them improve their conceptual understanding. And they enjoy them. I've never had a student tell me my homework is fun, but I've heard students say OEMPs are fun. And they say they want more like this. So this is just from one semester, but 6 courses at 5 institutions, but good feedback from students and faculty about the value of these OEMPs. So on the research side, what we're doing is we're looking at what does emerging engineering modeling judgment look like? What are students exhibiting when they are doing these problems? And so to study this, we conducted, Professor Swenson at Buffalo conducted 34 retrospective interviews with students in 6 classes at 4 universities doing 4 different OEMPs. So a lot of data. We went through 5 cycles of qualitative, iterative, adjudicated coding based on a taxonomy of established professional engineering judgment, really engineering modeling judgment, from Julie Gainsbourg, an ethnography of some structural engineers out in California, I think. So we did that 5 cycles of coding. We came up with 4 types and 15 subtypes of emerging engineering modeling judgment. So when students are creating the model, they're using 2 of the types of engineering judgment. One is making assumptions about the representation. What assumptions do we have to make? And then using technology tools. How do we use CAD or Excel or other tools like that to help us in our modeling? Then students go through, they use the model, they calculate an answer, and then as I said, they have to assess the model. So they assess the reasonableness of their answer, of the model as provided by the instructor. We have students recognizing and saying things like, we ask them, how do you know your model's reasonable? And they're like, well, we're sophomores, and our instructor gave us this assignment, and the assignment as it was given to us really wasn't reasonable. It's not really realistic. We also have students overriding a calculated answer. So some students, when they find that the landing gear leg is 2 millimeters in diameter, they just say, well, that's what the math says. I'm going to put that down. Other students say, well, I'm not really comfortable with that. I'm going to round up, right? I'm going to give a bigger number. I'm going to use this calculation essentially as a basis for my decision, but I'm going to use my judgment to choose a larger value for this landing gear or whatever. So those are 4 of the ways that we see emerging engineering modeling judgment. So this is our full taxonomy. I am talking a lot, so I'm not going to go through it all. But this is in a paper that we have submitted to JEE. I'd be happy to send you the preprint if you're interested or talk to you. But we talk about those 4 large categories and then the subtypes of how students engage in these types. So like, how do they make an assumption? We look at all the different justifications they use. So are they considering like a hypothetical client or manufacturer? Are they, doing research for the class? Are they like going to a pool and looking at the distance between the ground and the water level, right? When they're trying to model the pool lift. Are they using their lived experience from outside the classroom? Are they trying to simplify the model? Are they trying to model the worst case scenario? So things like that, capturing the justifications that students use when they make assumptions, and then also capturing what aspects of reasonableness they assess, and then why do they override a calculated answer when they do, and why do they choose to use technology tools? So what are we doing with this taxonomy besides publishing it? Well, we're using it to create better OEMP scaffolding that engages all students in engineering judgment. This is the part of the project that Professor Swenson is really working on at Buffalo. Here at Michigan, we are working on teaching this taxonomy to faculty, right? So we say, this is what your students are going to be doing. Look for this, notice it, then you can respond to it when they see their students displaying engineering judgment, a way of, it's called responsive teaching, a form of formative assessment that happens very much informally in real time during the classroom in conversation with students. So that's what we're doing here at Michigan, and we will be soon recruiting faculty to do OEMPs here at Michigan once I have time to write the IRB. And now that this presentation is done, I will have a bit more time. We are also applying it to project teams, which is a really cool thing that we've been doing. So if you have this continuum with expert professional practice on one end of a spectrum and sort of sophomores doing their first open-ended modeling problem, student project teams are somewhere in the middle. I don't think they're right in the middle. I think they're closer to the sophomores, but they are a step between the sophomores and the expert engineers in terms of the engineering modeling judgment. Project teams, so we're talking here like competition teams like Solar Car, Baja, the Human-Powered Submarine team, which is the one I was on as an undergrad. These problems, they're more open-ended, they're more ill-defined than OEMPs, but they're still structured more than engineering practice. They're still smaller problems, and the professional societies that organize these competitions will often, they'll create guardrails or boundaries for the students in which to work. Also, so we are currently working, I'll show on the next slide what we're doing, but we're finding some really interesting differences between students on the OEMPs and the project teams, because on an OEMP, students only knew one theory of behavior, and so they had to really model the representation. They only know Euler-Bernoulli beam theory. On a project team, they can choose the theory of behavior, right? Students on a project team can choose, do I use the material from my 200 level course, my 300 level course? Do I need to go and find a new textbook and apply graduate level theory? There's a lot more decisions that students have to make when doing the mathematical modeling. Also, when students are doing OEMPs, they're only really doing analysis, but project teams also have this design component. So there's another aspect there with what project team members are doing and how they're employing their engineering judgment. So we have 11 interviews with 12 students on 7 project teams. And what we're doing is we're doing our qualitative, iterative, adjudicated coding again. We're starting with our emergent engineering modeling judgment taxonomy and essentially remixing it. We've done 2 cycles of coding. We still have some to do. We're not done yet. We still have 4 main types of engineering modeling judgment, but we are modifying some of the subtypes. We are adding some subtypes of engineering judgment. once again, I don't expect you to look at the details really. What what I want you to take away is that there's some red on this figure. So we're modifying things, we're adding things, right? We're sort of remixing this taxonomy to say, okay, well, we know what students can do in a classroom when working on an open-ended modeling problem. What can they do when they're working on a project team? And there's a lot of similarities, but there are differences because the context is different. All right, so as I said, sort of all of the work we do in the lab is really predicated on this idea that engineering practice is messy and most engineering science courses are tidy. But I argue that engineering science courses can be messy too. And so we do that, we work at that through design-based research, we build this up. And as I talked about specifically with engineering modeling judgment, we have the research side. We're saying, okay, what are students thinking? What are they doing? How do we convey that to faculty? And we have also developed this new type of problem, project-based learning that encourages students to engage in engineering judgment. And we will be continuing to work on faculty development. We ran one workshop last semester, and we learned a lot about what to do differently next time. That's also useful as well. All right, so I want to give thanks to all the wonderful people who helped me with this. Teamwork does make the dream work. And there's amazing people from all over who have helped me with this work, and I am indebted to them. And so I'll conclude with the guidance of the great Noel Perkins, who would tell me to stand here and demand that you ask me a question and not let you leave until you do so. So thank you very much. Yeah. I will take questions. We can see if some come on chat, or maybe Karen, if you want to revoice those. Yes.
So I know how you mentioned that like these messy engineering problems can cause students anxiety because they haven't seen them before. Do you think introducing these problems in their early courses, like having open-ended design problems in their engineering 100, as well as like most of their engineering sophomore level courses and junior level courses, will reduce that anxiety?
Yes. Okay, so I'll elaborate, but yes, I agree. And that's a very good point. And thank you for bringing that up, because I do want to say more about this. So yes, I think that's really important, right? I also think that like some anxiety, if it's controlled and has an endpoint, is not bad. Like I think it's okay to give students like a constrained open-ended problem and like let them struggle a little bit. Now you have to like end it, and you have to make sure that it's a safe space to struggle and that their grade's not going to tank. But like a little bit of that I think is good, because that's really where learning happens. And I agree, like I think ideally you would have like a really tightly constrained open-ended modeling problem in sophomore year. And then you can have another one in junior year that's maybe a little bit more open, right? So I definitely think, and Professor Swenson is doing research with Emma Treadway, who is a professor at Trinity University in San Antonio, also a Michigan mechanical engineering PhD alum. They're looking at this idea of epistemic affect, which are like your feelings about knowledge and learning. And they find, yes, students might be anxious and struggle with the first OEMP, but they do really well on the second OEMP. Yeah, so the more you do this, the better it is, because it's another skill to learn. Yeah, and so that's, thank you for asking the question to give me a chance to talk about that. Yes.
This is a question from the chat, Aaron.
Okay.
I have seen students reject PBL problems in my statics mechanics courses as they are not like other assessments. How do you present these problems in classes?
Oh, good question. Yeah. So how do you present them? I think that you try to work to connect them with the material, right? You say like, okay, we learned about this, and now I'm gonna have this OEMP or project-based learning based on the material that we just learned. I think really explaining why you are doing these is also really valuable. So saying like, we are doing, maybe you don't like give an hour-long lecture about engineering judgment, right? But being like, in statics, you learn constrained problems, and it's really useful to look at to learn just how the equations are applied to closed-ended problems. That's not what engineering is like. When you go get a job, your boss will never ask you to find the one answer to a problem. You are going to need to take an object and make a model, right? You're going to have to think about all the assumptions and everything. And so we're going to do this one problem to help emphasize that. And so I think setting it up, explaining why you're doing it, why it will benefit students, I think that is one thing that can help to reduce the resistance. There's also a lot of good research on student resistance to active learning and ways to get around that. Professor Finelli's done a lot of that. I think a lot of those recommendations also apply to introducing this type of problem as well. And I think too, right, I would also encourage you, right, how do I say this? Sometimes students don't know what is best for them, I guess, right? And if you have resistance, but you know that this is good for students, yes, you should certainly respond to their feedback and work to make it better. And maybe you are giving them too much to do, or maybe you're giving this right before an exam and they're just so busy, right? So you should definitely listen to student feedback and make improvements to better their learning. But at the end of the day, I think if you are convinced that something is good for students, you should keep trying it and keep working at it. And, there's always room for improvements. And I have found as well, when I talk about this stuff, the first time it's really hard. And then you just keep doing it more. It's like muscle memory, right? Every year it gets easier and you get better at it. You get better at connecting it. But whoever asked that question, I do want to uplift that as certainly a challenge. That is a challenge, and it's something that you have to work at, and something that you have to learn how to do. It's not just that all PhD graduates know how to put project-based learning and engineering science courses. That was really long. Sorry about that. Yeah, Rob.
Have you or will you look at that taxonomy? Thank you. Have you or will you look at that taxonomy and look at how engineering professionals exercise engineering judgment?
Yeah, if my career grant is funded. So yeah, that is what I would really like to do. I think there is a dearth of literature studying practicing engineers. You've got Shane Brown at Oregon State, and maybe another person or two. Very few people are looking at practicing engineers, but that's what we want our students to be. And so we should look at them and study them. And so, yeah, we have questions right, Julie Gainsbourg's work is tremendous. It's also 2 decades old, and the nature of engineering has changed. So how do they handle messy problems? How do engineers think about the socio-technical effects of their work, and how do they deal with ethics? I think there is a very fruitful area of research there studying practicing engineers, and that's definitely something I want to do. So please don't steal that. Where's the camera? I need to get tenure. So a very important question, yeah. Well, you've asked questions, so I'll let you leave, but is there no more in the chat? All right, well, I guess I'll conclude there. I mean, my email is up on screen, so if you have more questions or want to talk, please do send me an email. If you're here at Michigan, we also have these macroethics lunchtime dialogues where we talk about macroethics topics. If you want to engage in that way, we had a very good discussion about environmental justice today. So you can talk to me about that, or you can convince Dr. Joe to organize an EER sub-discussion. So multiple options. Thank you.
Thank you again, Professor Johnson. And just to remind everyone, we have one more seminar coming up this fall. We're going to host Professor Robin Fowler at our December seminar. So hope to see you all there. Thank you.